Welcome to Quantum Qubits, and in today's video, I'm going to discuss quantum computing with Qiskit. So Qiskit is a open software that everyone can use, and it is developed by IBM, and you can simulate your quantum processes and different quantum algorithms through using Qiskit. So Qiskit is a very important and uh, pivotal tool for students and researchers. Um, and you can learn different kind of processes through this. So in today's video, I'm going to discuss how to initialize your Qiskit in Jupyter Notebook and how can you initialize qubits and bits in Blocksphere, and also how can you initialize your qubits using some simpler tools and simpler mathematics like linear algebra. And also we'll see that how the measurement in quantum realm differs from measurement in classical realm. And what is the fundamental uh, difference between quantum computing and classical computing? So let's start with initializing our notebook. So I have opened the Jupyter Notebook, and it has opened in my Chrome, and I'm going to initialize a notebook. So this is initializing will take some time. So it has asked us to select a kernel. So I am selecting a default kernel that is Python. So we are going to use Python in Jupyter Notebook, and we will use the Qiskit uh, in our Jupyter Notebook. So first of all, we have to install the Qiskit in our environment. So the command we have to give is pip install Qiskit, and we have to enter shift enter. So our command has initialized and is running. So it will take some time. So it has said that already the requirement already satisfied because the Qiskit is already installed in my environment. Another big command we gave is to install Qiskit visualization tools to this command. Solution. And again, shift enter. So it is running. For Windows 3. So Windows will be some warning, so I will install it. So some of the packages related to Qiskit visualization have been installed in my environment and my setup. And in further command, we can see that which Qiskit version we have on our environment or on our Jupyter notebook. So pip show Qiskit. I hope I have entered the correct command here. This So again, it has said that we have installed Qiskit and the version is 2.0.0, and there's some additional details related to where it has installed and other uh, packages details here, and you will see that. So we would not go in detail uh, to these additional details. So first of all, I will try to initialize bits and qubits. So you know that bit is a classical element, and it could take either of the value 0 or 1 in binary case. Uh, and qubits are fundamentally quantum objects and quantum elements, and they are inherently different from the bits as they can exist in 0 and 1 states simultaneously. So this is the fundamental uh, uh, difference between qubits and bits. So I would first initialize some parameters related to the qubits to define the qubit parameters parameters for superposition. So we know that superposition is you can say the parent property and inherent randomness of the qubit as qubits can exist in 0 and 1 states simultaneously. And we do not know before the measurement what we are going to get, but we can predict with some probability that what we are going to predict or what we are going to get after the measurement. So this uh, this is usually predicted by uh, the weights of the different elements, usually called probability amplitudes. So there is some constraint on probability amplitude. So first of all, we have to initialize some of the or we taught some of the tools like NumPy, where we can do some numerical calculations, and for math, that is the built-in library from which we can import some important mathematical tools like Qiskit and our methods will going to help us and data. So we have to initialize our probability amplitude in the case of qubits. So I was talking about that there is some constraint on qubits or probability amplitude, like they have to be normalized. And normalization condition is that there's some of their squares should be equal to 1. So uh, A and B could be anything until their square side is equal to 1. So this is the constraint on our probability amplitude of the qubits. So we could check this condition that if round function of our A plus uh, B is not equal to 1, then we could generate some warning uh, message that your qubit parameters are not normalized. So whenever we have that condition that the power, that the squares of the A and B and the sum is not equal to 1, then we are going to give the program of our is going to give a warning message that the qubit is not normalized and we have to uh, adjust the parameters. So first of all, I am going to again, uh, we have to give this well, that's the probability amplitude of the given qubit. That's, I will initialize bits and I'm going to use the dictionary. So dictionary in Python is a tool uh, that is a kind of list in which we have some elements that are assigned uh, a key, a particular key. So we can keep the contents of the list to using the key that is unique and particular to particular to a single element of the system. So we are going to use that concept of Python to initialize some units and bits. So bit zero is going to be a key of 1 pi array of zero. This is our first bit. And next, again, similarly, we could initialize. We could create another bit one in form of the array of 1 pi. And it is zero, usually denoted as is 0 and 1. So these are column vector of dimension 2 in that case, and again, we can use the bracket notation to divide our bits. And again, we know that it is an array of 2 dimension and from 0 it is 0, 1, 1, 0, sorry. And similarly, much more to do this time. I will give a 1 bit. 1 bit is shown as 0, 1. And now I'm going to class our qubits. That is the superposed state of 0 and 1. You can write it as 0 plus this entire array. Again, that we initialized earlier. So this term, we have initialized a dictionary, and we have given the elements to the dictionary, and each element has a particular key and given as, as in this string form. So first of all, we would see that how we could print contents of our dictionary. So I will print the vectors here. So for print, we have to retrieve each of the content of the dictionary. So I'm going to use the loop here. That is the for loop. So for B in bits, that is the dictionary above, that we have initialized above, and I'm going to print it. So print the what is the each element of the and well, we'll make it more explicit and the and the output more visually appealing. So so it is going to give each element of it one by one, and I'm going to write the elements of the way to the three decimal places. And then to give the space between each output, I have run this command. So let's see what we are going to get after this. So this is our vectors that we have initialized here, and you could see that it's quite amazing to see how can we simple bit of Python language, Python commands, and Python coding to write some arrays and initialize our bits and tables. So this is the uh, trend of the output of the dictionary that we have been initialized to. So that's good. So now I'm going to measure qubits and see what are the probabilities that we have when we are going to get output 0 or 1 when we measure the bits or qubits. So in order to make it more appealing, I first give it a string measuring our bits and qubits. And then I some kind of a hash map. Is enough. Uh, First of all, to have all the probabilities of the measurement, I am going to visualize empty, an empty list. So this is our empty list, and I will append all the probabilities that I'm going to get after the measurement in this probability list. Again, I have to use loop, that is the for loop, in order to retrieve all the elements from the dictionary that I have initialized earlier, one by one. So for these bits, I want to see what I have got from the bits in B. I will first print B, then I will say that print probability of value. Hope I have it's not mechanic spelling mistake. Probability, yes, it's right. Probability of category. So for dig, so dig is any kind of index, that's the domain box, and it is it is going to be either 0 or 1. So in order to make it that case, we have to retrieve the length of the vector that we are using. So each vector has length 2. So either dig could be 0 or could be 1. So I'm going to use that index. And the probability, we know that it's the square of the associated with the 0 or 1. So in that case, probability of B, that is the each element of B, is going to be power of bits and bit. So this means that we are going to take the power of the bits B and each element in the vector that we have here. So the first element is going to be 1, and then the another element is 0. So this index dig is initializing or retrieving retrieving the element 0 or 1 from that vector. So this is the case for it, and I'm going to get power of 2, so I have to make it here. So print dig. So dig would be either 0 or 1, and have to make here some executed remarks. we want to show that the result or the output would be numbers, and the decimal places it would take should be equal to 2. So I have to make it explicit here by using this command, this probability of p that we have calculated above should be multiplied by 100, because here we are going to the probability some decimals that would be equal to 1 or smaller than 1, and in order to take or in order to make it from a percentage, I have to multiply it with 100, and then I would need a diagram here. So let's run it and see what are the probability measurements and in the case of the bits and the qubits. So again, you could see here bit 0 has probability of getting 0, 100%, and for 1 it is 0%, and for bit 1, the probability of getting 0 is 0, and the probability of getting 1 is 100%, and for 0 and 1 bit similar. But in that case, for the qubits, we can either get 0 and 1 with probability of 50% for both. So qubit, we know that the state of the superposition, and we could either get 0 or 1 after the measurement with the same probability. So there is the equal chance to get 0 and 1 after measuring the qubits. So this is the fundamental difference between qubits and bits. So now see, now we have to visualize bits and qubit, how does they look like in some kind of space. Because we are using some abstract remarks to say these are qubits and these are qubits. So now we want to visualize that. So in order to visualize them, we have to initialize first some tools that we are going to use. And for math, we have to import sine, cos, phi. And in a minute, I will show that why they are important, why we are initializing these tools. And import, we know that we are going to use some kind of linear algebra tools, plus NumPy, and on Qiskit, we are going to send visualization tools. Visualization import plot blocks block for I Python display import display. So we have initialized our is that we are going to need in order to visualize the qubit and bits in our block sphere. So block sphere is a kind of a sphere, and we could use spherical coordinates to visualize the bits and qubits in our block sphere. And this is the very essential tool in order to visualize the qubits and bits, and even we could visualize the operation that we are going to perform in on our qubit centers. So it defines the composition, superposition, zero phase. So again, we are going to use the dictionary and keys of the dictionary are the name of the numbers. So theta is equal to as 5, 2, and 5 is 0. So we are going to take phase angle to be 0. So it would make the visualization and the whole process much more simpler. So define classical language. So again, that we have used earlier, we are going to use uh, dictionary in order to initialize our parameters. So bit 1, bit 0, so, uh, the theta uh, 0.5 would also be 0 for 0. So I want to put it as kind of half bit and for bits. So bit 1, you know that it lies at the opposite pole on the clock sphere. So you are going to give it theta value of 1 and again the 0 bit broad recognition. Again, uh, similar parameters as bit 0 and bit 1 will have same parameters as the classical bit, that it is going to have theta and phi. Now we have to initialize the parameters of qubits. So qubits we know at a simple state of 0 and 1. So we can plan our parameters accordingly. So uh, you know that we have already initialized our parameters for qubits of our angles. We could again use it here. So this we are done with initialization of our parameters for qubits and bits in order to visualize them. So in order to retrieve the contents of the dictionary one by one, we have to use the form. So theta for bit in bits, so bit will uh, one of the element, and we can uh, we can get it from bits that from above. So theta would be bits from one bit, and again the particular value from the key theta. And phi will again similarly could be retrieved from the same method from the key phi. So theta and key phi and phi are the keys, and we could retrieve the information about about them from the dictionary method of retrieving the elements from the dictionary. So we have also to initialize the block factor. Block factor would be in terms of the spherical coordinates. So first cos phi, which is sine phi or sine theta instead, and then sine phi multiplied by sine theta. In the last C in Cartesian coordinates corresponds to cos theta in and spherical coordinates. So we are going to draw the block sphere, draw block sphere vector, the block sphere. So this plane it is going it is going to get two arguments. So block block vector block vector two arguments block. Each block vector is going to get the corresponding title equal to either 0, 1, cat 0, cat 1, and cube and compute quantum state. So you know that A is equal to cos theta by 2, B is equal to this. So we have to use the complex notation here. That's why I'm going to use C now, exponential of 1 j. J means iota here. So we usually denote iota as I, but phi from syntax we have to use j because it is specific for iota here. Theta phi have to multiply as phi sine theta by 2. State vector, know that. So now we have to print the following things. So we'll print command and now I will have my print command. So F state vector for it is false to we are going to do something something kind of more descriptive in order to make it more easy to uh, visualizing. So state vector that we have initialized above just so this command is going to give the explicit form of the state vector that we have that we are going to print that we are going to visualize in block space. So This command will give us the block speed visualization, and this command will give us the explicit form of the block code or the state vector that we are going to visualize in block sphere. So let's enter print enter or shift enter. So I have made sample state setup. Oops. Yeah. So this it has initialized. Okay, I'm getting some kind of mistake. Oops, got a mistake. So I have to identify school block control dot output communities given source. So I have done some mistakes and I have corrected it now. And you could see that we could visualize our block sphere through the same code uh, that we wrote above. So zero corresponds to a kind of a pole and kind of a north pole, and one corresponds to south pole, and again we had zero for north, we had one for south, and our qubit uh, corresponds to kind of a equator because it has both the parts of zero and one, and both parts are equal. So using these codes and these simple tools from Qiskit, we can visualize uh, our qubits and bits more efficiently. So this is for today. We will see that what we can, what we can learn in our Qiskit series. So bye bye for now.